Let's talk about Laplace transforms. They're named after the great French mathematician Pierre-Simon Laplace. Suppose we want to solve the initial value problem dy dt equals y minus 4e to the negative t, y of 0 equals 1. We've seen before how to solve this. This is a linear first-order differential equation, so we could multiply both sides by some integrating factor and then integrate. But here's another way to solve such problems. Use Laplace transforms. Given a function y of t, the Laplace transform of y of t is denoted L of y of t. We always use this fancy script L. And that's defined to be the integral from 0 to infinity of y of t e to the negative st dt. And we can represent that as capital Y of s. Some books use capital F of s for all s for which y of s is defined. For example, find the Laplace transform of e to the t plus 7. The Laplace transform of y of t is L of y of t. It's the integral from 0 to infinity y of t e to the negative st. When we replace y with e to the t plus 7, this is what we end up with. And now we can combine those exponents. We get the integral from 0 to infinity e to the t plus 7 minus st. Okay, so this is the integral from the previous page. We can factor out a t. We have the integral from 0 to infinity of e to the 1 minus st plus 7. We're just factoring out the t. And here s is greater than 1 because if s were less than or equal to 1, this integral would diverge. It would just add up to infinity. So if s is greater than 1, then when we integrate this, we end up with the integral of e to the 1 minus st plus 7 over 1 minus s. Y over 1 minus s, because 1 minus s is this constant that's out in front of t. So when you integrate it, you just divide by 1 minus s. Oh, we evaluate that at 0, and we get, we evaluate that at infinity, and we get 0. We evaluate it at 0, and we end up with this. I know ordinarily, we replace infinity with b and look at the limit of the integral as b approaches infinity. So when we simplify this, plug in 0 for t, and we end up with e to the 7, negative e to the 7 over 1 minus s. If you put the negative sign on the bottom, that's e to the 7 over s minus 1. Okay, but it turns out there's an easier way to evaluate Laplace transforms for various functions, and that's just by using a table. So suppose we want a Laplace transform of each side of this differential equation dy dt equals y minus 4e to the negative t, y of 0 equals 1. Again, this is the initial value problem that we saw earlier. So we take the Laplace transform of each side. The Laplace transform of the left side looks like this, and to evaluate the left side, we just use these formulas. L of y of t, we're just going to call that y of s. L of y prime of t is sy of s minus y of 0. And L of y double prime of t is s squared y of s minus sy of 0 minus y prime of 0. So this left side, L of dy dt, that's just going to be, sy of s minus y of 0. So that's what the left side is. Now the right side is L of y minus 4e to the negative t. To evaluate the right side, we use these formulas. It turns out that the Laplace transform of the sum is the sum of the Laplace transforms. That's just based on the basic rules of integration. And the Laplace transform of a constant times f is that constant times the Laplace transform of f. Again, here we're assuming k is a constant. So the right side can be broken up as L of y of t plus L of negative 4e to the negative t. We can pull the negative 4 out, and we get L of y minus 4 L of e to the negative t. Okay, so here's what we want to evaluate. L of y is simply y of s. That's easy enough to evaluate. That's good. Minus 4 L of e to the negative t. Well, there are tables we can use to evaluate those two. Here are the tables we're going to use. We've seen those before. We're dandy with those. Now again, we want to evaluate L of e to the negative t. So this is the one that we want. L of e to the at, 1 over s minus a. In this case, a is negative 1. These other formulas come in handy for various other problems. Here's some for sine, cosine, hyperbolic sine, hyperbolic cosine. Okay, so again, when we use that formula for L of e to the negative t, we get 1 over s plus 1, because again, your s was negative 1. I'm sorry, your a was negative 1. So L of e to the at, 1 over s minus a, plug in a equals negative 1, and you end up with 1 over s plus 1. Okay, and that's what we'd end up with on the right side. Now the question is, well, that's great. Now how do we solve it using Laplace transforms? Well, next time we'll look at inverse Laplace transforms and see how we can solve this initial value problem.